Okay, apologies about that. Sometimes the videos get cut off for seemingly no reason, so I apologize. But I didn't get too far before I realized that the video was cut off, so that's good. We were just saying that it was interesting that the work done by the applied force is the same whether we pick the object straight up or we use a ramp to pick it up. So the obvious question is, what the heck is the point of using the ramp? I'll get to that in just a second. The one thing I did before I realized the video was cut off was I calculated the new gravitational potential energy at this height. Unsurprisingly, since it's the same object and we are still getting it up to the same height of 4 meters, the gravitational potential energy is the same at the end of using the ramp as it was when we picked the object straight up. The conclusion that we are supposed to make here is that the amount of work done to raise an object to a certain height does not depend on the path taken by the object. All that matters is the change in height of the object. So we might say that it is path independent. The path of the object takes does not determine what the final, how much work was done. It's simply what the difference in height is between the initial and final points. And same goes to the gravitational potential energy. The gravitational potential energy is the same no matter what the path was taken. It just depends on what the change in, what the mass, the acceleration, what the mass, the acceleration due to gravity, and the change in height are. Now, the reason you might want to use a ramp instead of just lifting something straight up, look at the forces required to lift the object. To lift the object without a ramp, Fa equals m times g. Straightforward calculation, but if the mass is very big, then it takes a lot of force. On a ramp, the applied force needed to lift the object up the ramp is mg times sine of theta. Now, what do you know about sine theta? Anytime you calculate the sine of something, sine of some angle, it's going to come out to be less than 1. So Fa on a ramp is guaranteed, if it's frictionless ramp, is guaranteed to be smaller than the applied force for just lifting something straight up. So interestingly, that's why ramps are nice to use. Not because they make you do less work, but because they allow you to use a smaller force, but the trade-off is the distance you have to, or the displacement you have to move the object through is greater. Here, we just had to lift the object up 4 meters. Here, we had to lift over 10 meters. So the force is smaller for a ramp, but the displacement is bigger. And humans are designed, we are designed to be able to exert small forces over big displacements. We are not designed to exert big forces over small displacements. So that's why a ramp is useful in a lot of cases. In any case, that's a little bit about linking work and change in gravitational potential energy. Let's go to the last part of this example now. Let's now say that the object were to suddenly fall from its height of 4 meters back to the ground. What would its speed be just before it hits the ground? Well, let's think about this a little bit. Here's where the object starts up. Here's where it ends. Okay, here's the ground. Here's where it starts. It falls down. Initial and final. Now, what type of energy does it have up here? It's got gravitational potential energy. And one thing that I want to clear up is it doesn't have gravitational potential energy because it's not moving. That's not true. It has gravitational potential energy because it's above the ground. Sometimes I get people thinking that an object that's not moving has gravitational potential energy. That's not true. Objects that are on the ground and not moving do not have gravitational potential energy. It has gravitational potential energy because it's up above the ground. At the final spot, right before it hits the ground, what type of energy does it have? It's got kinetic energy. So, at the top, it's got a gravitational potential energy equal to 1,962 joules. Then it falls. During its fall, we know as it moves down, the gravitational potential energy should go down because the height is decreasing. Decreases, and what else happens as it falls? Well, the kinetic energy increases because it's speeding up. So what you have happening here is the gravitational potential energy is being turned into the kinetic energy. And what force is causing this? What force causes it to fall? It's the force of gravity. Gravity is doing work on the object, and it's changing that gravitational potential energy into kinetic energy. at the bottom, all energy is kinetic energy. So the kinetic energy equals 1,962 joules. So here's what we have. The potential energy at the top must be equal to the kinetic energy at the bottom. We already know the potential energy at the top is 1,962 joules. We can solve for the kinetic energy at the bottom, we already know the kinetic energy at the bottom is 1,962. We can solve for the speed. 1,962 joules equals 1/2. The mass was, I believe, 50 kilograms times v squared. I solved this for v squared by taking 1,962, multiply by 2, divide by 50, and then take the square root. And I get that the speed of the object is 8.86 meters per second. So look, I solved for a kinematics variable using energy. I want you to think about that for a second. Is there any other way that we could have found the final speed? Think about kinematics. We know how far it fell, we know the initial speed, and we know the acceleration due to gravity. Imagine if I just did this. Vf squared equals vi squared plus 2ad. The initial velocity is 0. The acceleration is 9.81 meters per second squared. The distance it falls is 4 meters. 2 times 9.81 times 4 equals 78.48. If I take the square root, look at that, I get the same thing. Now the point of this isn't to show you that, a lot of people say, well, I just use the kinematics. That seems a lot easier. Yeah, that's the case. I think it is easier to use it there. But you could also figure this out using energy. And that's important. It's important that we could do that. Because imagine if we got a different answer for the final velocity using the concepts of energy. Well, then one of them's got to be wrong. Either energy is wrong or kinematics is wrong. It's good that you have the same thing. And there are cases where using energy to find the final speed of something is much easier or the only way to find the final speed as opposed to using kinematics. So, what I'm intending to show with this example, the object falling back to Earth is a situation in which we say that energy is conserved. When energy is conserved, that means that all the energy that's present at the beginning, all of the initial gravitational potential energy, PEG, is converted to kinetic energy at the end. All the energy that was present at the beginning is still present at the end. And we're going to see many more examples of that in a week or so when we start talking about conservation of energy as a topic by itself. The last type of energy we're going to talk about today is potential energy of a spring potential energy or elastic potential energy. The definition of this is energy that is associated with the stretching or compressing of a spring. And remember, any object can act as a spring. Any object that can deform its shape can act as a spring. How does an object gain elastic or spring potential energy? Well, a force stretches or compresses a spring some distance, or some amount, I'll say. Okay, so if you take a spring, I've got a spring here somewhere. I did have a spring here somewhere. Well, this will work. Rubber band. Rubber bands are springs. If I take this rubber band and stretch it, I am storing elastic potential energy in the spring by virtue of the rubber band has had its shape deformed. If I had a spring here, I could compress the spring and also store energy. You can't really compress a rubber band, though, at least one like that. The derivation is a little weird for this one, okay? And the reason it's weird is because of how the spring force works. You'll remember that the spring force equation is Fs equals Kx. It's on the reference tables. That implies that as you stretch or compress the spring, the force that the spring exerts changes, and the force that you're exerting on the spring itself changes. So we have a little bit of a weird situation here. Let me draw a free body diagram. Here's an object. The object is attached to a spring. Let's say you pull on the object this way. The spring will try and pull the object back that way. And the force from the spring will change as you stretch the spring out more, so that you'll need a bigger and bigger applied force. The net force equation in this case is Fa, minus Fs equals Max. Let's do a situation where we've pulled this object out a decent some way and we're just holding it there. If we're just holding it there, it's not accelerating, that's 0. The applied force is equal to the spring force at this point. It's equal to K times X at this point. Now, we need to note, as we mentioned before, since the applied force is changing as X, or in this case we could also say D, the displacement changes, when we're trying to calculate the work done by the applied force, okay, the applied force and the displacement are in the same direction. When we're trying to calculate the work done by the applied force, we have to realize that Fa is changing. As we pull the object out more, the applied force gets bigger because the spring force gets bigger. So here's what we're going to do. We're going to take the average value of the applied force. Now, let's think about this. So we have a spring. We'll use a rubber band as an example. We have an object tied to the spring, and we're pulling the object to the right. Now, when the spring is not stretched at all, we don't need any applied force to hold it there. As we stretch it farther and farther, we need more and more force in order to hold the object there. So the applied force is growing. The applied force is going to grow until we get it all the way out to our maximum stretch. If we want the average applied force value, well, if it's 0 here and some maximum value out here, the average should be right in the middle, somewhere between 0 and the maximum. In other words, half of the maximum value. So here's what I'm going to say. The average applied force value, remember this symbol means average, equals 1/2 of the applied force when fully stretched at X. So what that means is that the average value of the applied force is 1/2, and let's see, at the maximum amount of stretch, the applied force is equal to K times X, K, X. The maximum applied force is 1/2 of K times the maximum amount of stretching. Well, if we come and plug that in over here, the maximum amount of stretching, that's the same as the displacement, okay? If the spring's stretched by let's say 2 meters, then that means that the displacement, the object moved 2 meters. So D is really the same thing as X. I get this. The work done by the applied force is equal to 1/2 Kx times X. If I have X times X, I can just write that like this, 1/2 Kx squared. That's the work done by the applied force. That work's got to go somewhere. Where's that energy being transferred? Where is it being stored? It's being stored in the spring itself, okay? When you stretch out a spring or compress it, you store energy in it. How do we know that energy is stored? Well, number one, work has been done. But number two, if I let go of the spring, it will snap back. That potential energy, that elastic potential energy that's stored in the spring, now becomes kinetic energy. So that energy must have come from somewhere. It's been stored in the spring. Since there's no initial energy, we get this. The work done in this case is equal to the change in the elastic potential energy of the spring, PES. And PES itself is equal to 1/2 Kx x squared. Right on the reference tables, right here. PES equals 1/2 kx squared, where k is the spring constant, x is how far it's stretched. Don't get it confused with the force on the spring. Energy and force are two totally different things. They are not the same thing. Forces are pushes or pulls on an object from another object. Energy is the ability of an object or system to move or potentially move in the future. Okay? It's some number that is going to be useful to us later on. So, the key takeaway here is that the elastic potential energy equation is 1/2 kx squared. Do you need to know this derivation? No. I show it because some people might be interested in it. Okay? Not everyone's going to be interested in it, but some people might be. The elastic potential energy is 1/2 kx squared. And by the way, these equations that we're coming up with, mgh and 1/2 mv squared and 1/2 kx squared, you might be like, okay, I know that we're deriving them, but why are they useful? Okay? Why do we care? We care because they allow us to solve problems. Okay? It's not just something new that we're trying to force you to calculate to work on math skills. You got to take me for my word right now. Those equations for calculating the different types of energy, they have uses. Okay? Using these ideas, we can solve problems we wouldn't otherwise be able to solve. As we go through the unit, you will see some of these ideas. But for right now, that's pretty much all I can tell you. All right. Our examples for elastic potential energy. A water balloon launcher has a spring constant of 40 newtons per meter. It is stretched back 1.3 meters and loaded with a 0.8 kilogram water balloon. How much potential energy is stored in the spring? This is very straightforward. The elastic potential energy stored in some spring is equal to 1/2 kx squared. K, we're told, is 40 newtons per meter. X, the amount it's stretched, is 1.3 meters. That needs to be squared, so don't forget the squared. 1.3 squared times 40 times 1/2. We get an elastic potential energy of 33.8 joules. If all of the potential energy in the spring is transferred to kinetic energy of the balloon during the launch, what is the speed of the water balloon when it gets launched? This is another conservation example. The potential energy of the spring equals the kinetic energy of the balloon. Remember, we know what the elastic potential energy of the spring is, 33.8 joules. The kinetic energy equation is 1/2 mv squared. 1/2, the water balloon is 0.8 kilograms, v squared. We solve for v. We get 84.5, we need to take the square root, and we get a velocity of 9.19 meters per second. So again, that one we could not have solved using kinematics. Okay? We couldn't have solved it because that force, as the water balloon launcher comes back to its normal spot, would be changing the entire time. The acceleration would be changing. There's no other way that we could have solved this except for using energy. Okay? So the fact that we're using this 1/2 kx squared, this 1/2 mv squared, the reason we're using it is because someone determined at some point in time, hey, if I multiply these things together in this order, I get something that is going to be useful. Okay, that's why we use this. I know it seems random, but that's the best explanation I can give you. We use it because it works. It's a nice mathematical tool. That's it for different types of energy, at least for mechanical energy. Next video, we will be talking about internal and thermal energy. Talk to you later.